Hello, welcome to this lesson on nuclear reactions. The question of the day, what are the four types of radiation? All right, I hope you said alpha, beta positive, beta negative, and gamma. We are now getting into nuclear reactions, and there are four types of nuclear reactions. And in this case, a very small amount of energy, a very small amount of matter is going to convert into a very large amount of energy. And this is all based on Einstein's equation E equals mc squared. And that is energy equals mass times the speed of light squared. And this is where the law of conservation gets a little bit fuzzy. It works in chemistry. Once we get into nuclear chemistry, about the nucleus as opposed to all about the electrons, matter and energy, according to this equation, are really two forms of the same thing. Energy compressed over and over and over again, really super dense and tiny, becomes matter, is more or less what this equation is saying. So matter can convert into energy. That is what a nuclear reaction is. We don't have the ability to turn energy into matter. That appears at this point to be something only nature can handle. But matter turning into energy would be a nuclear reaction. All right, so again, the E equals mc squared equation kind of loosened up what the law of conservation actually means. And it's kind of just that the matter and energy are two different forms of the same thing. And we can change between forms, but not really. We can do matter to energy. That's it at this point. The only way that we know to convert matter into energy is by a nuclear reaction. Regular old chemical reactions like your synthesis, decomposition, let's say substitution, combustion, those things will release energy a lot of the time, but nowhere near the magnitude of a nuclear reaction. The first type of nuclear reaction is called a natural transmutation. And in this case, your radioisotope is not stable. So it is going to degrade over time, and it will spontaneously change from one element into another because it's just emitting stuff out of the nucleus. And the goal here is for your radioisotope to become stable over time. It's kind of related to half-lives, which we will talk about later. So in this case here, we have carbon-14, which is known to be a radioisotope and not very stable. It is emitting beta particles, and in doing such, it is going to become nitrogen with a mass number of 14 and atomic number of 7, which we know to be the most common isotope of nitrogen, and thus far more stable than carbon-14. Here we have an example of uranium-238. It is degrading, emitting alpha radiation, and becoming thorium-234, which still not that stable. The thorium-234 will probably also degrade, but the uranium-238 in this case is becoming more stable. We can also have artificial transmutations where we kind of help this reaction to happen. A lot of the time you will see it written as bombarding a nucleus, and that's because a lot of the time we're going to launch alpha particles or neutrons at an unstable radioisotope to get it to kind of break apart. So in this case, we have beryllium-9, and we are shooting alpha particles at it, think like Rutherford, and it is going to degrade into carbon-12, and carbon-12 is the most common isotope of carbon, so it's going to be very stable. There's also going to be a rogue neutron flying around here. That neutron also will probably kind of circle through this reaction vessel and go and bang into another beryllium and kind of just keep it going, because it's very rare that we have just one beryllium particle. One particle of anything even. So this is just going to continue on and on, but the idea here is that it's artificial because a scientist is kind of poking and prodding this radioisotope to get it to break down. It's not happening naturally on its own. So here you can see we have this alpha particle coming in and smacking into, I don't know what this is. I think the greens are neutrons. So this would be, yes, this is the beryllium. This is beryllium with not enough neutrons to be the reaction from before. But still, you can see that they're kind of like smacking into each other and making a new nucleus, and they have that rogue neutron just kind of flying around. So this is the idea here, is that there's two reactants as opposed to the natural transmutation where you have just the one reactant. Fission is what's going to occur in nuclear bombs. So what happens is you have a really, really big nucleus. This is not just nuclear bombs. This could also be your regular form of nuclear power. And what happens is that you have a really big nucleus, maybe like a uranium, a thorium, plutonium, something in the big F block down at the bottom. So here we have uranium-235. And what happens is that you are going to fling a neutron at it and you get a chain reaction. So that neutron is going to smash into a uranium and split it up. And in this case, it is splitting into a tellurium and a zirconium with 2 neutrons just kind of floating around with it. These sometimes can be recycled and you can repeat a fission. It kind of depends on what radioisotopes are coming out here. The idea is that in a perfect world, the things that come out of this fission reaction would actually be pretty stable so that you don't have to worry about nuclear waste all that much. But the uranium-235 is going to be split by bombarding it with typically a neutron. Then what happens is that these 2 neutrons that pop out will find another uranium to go smack into, and it creates a chain reaction. It happens very, very quickly. We use this reaction for nuclear power, and when done properly, it can be very safe, but when done improperly, it can be very unsafe. Okay, so here's an example of it happening. Here we have the uranium, and this little neutron is going to come, and because this nucleus is so unstable, the neutron does not have a lot of difficulty popping it open. And when it pops open, it's splitting. Here it's a barium and a krypton. And it is going to release a heck of a lot of energy, and it's coming out in the form of gamma rays in this case. And there's also going to be some neutrons that pop out, and these neutrons are going to go hit other uranium atoms and get the same thing to happen again. So at this point, you just kind of like start over, and you have this neutron here that hits the uranium, that splits, and 2 things are going to happen. This barium krypton byproduct, whatever it is, this might be a radioisotope that you could then repeat the process for, or it could be something super stable. Either way, typically there's going to be a lot of energy emitting from here, and you have nuclear waste. There is a lot of research happening in terms of what to do with nuclear waste, because if you do nuclear power well, it's very effective. So the idea is if we can handle nuclear waste or get it to no longer be emitting radiation, then we can get it to be even safer. And with that, we would have a heck of a lot of power generated from just a small amount of matter. The last of the 4 reactions is called nuclear fusion, and this is what happens in our sun and in stars all across the galaxy. We are going to have very light nuclei kind of squeeze together. They're going to fuse together, and they are going to make larger elements. To our understanding, this is how the elements were initially made in the Big Bang and in subsequent stars. Hydrogen is going to fuse with other hydrogens to make heliums. Hydrogens and heliums are going to fuse together to make bigger heliums or lithiums. We can fuse really any elements, but the most common ones that you'll see are hydrogen and helium because that's what happens in our sun. So here we have deuterium and tritium. Tritium. I never know how to pronounce this. It's a hydrogen with a mass number of 2 and a hydrogen with a mass number of 3. And they are going to fuse together. They generate a lot of energy as they do this, and we will be left with helium. And this is actually a pretty great thing to happen because these 2 hydrogens are not very stable, hydrogen 2 and hydrogen 3. Radioisotopes. When we can fuse them, we can get helium, standard regular old helium. And as long as this has electrons with it, it's very stable. In this, we can also get some neutrons that may circle through and add to the mass of other isotopes that come out of this. But all in all, this is a really great reaction because the contents are very light, very small, easy to come by. Hydrogen is all over the place, so it's not so bad. I don't know if this or uranium would be safer for nuclear power, but I know that we could use both. I know that we also more commonly use uranium, but that may be due to availability. Okay, now I know that fission and fusion sound really, really close to each other. So just looking again, fission is when you have that tiny little neutron go in and hit a big nucleus and it splits into things that are smaller, but kind of like middle of the periodic table. And fusion is where we have tiny things like hydrogen and helium come together and make something a little bit bigger. Also important to realize that fusion is sometimes used in chemistry to describe freezing. So just be very mindful of the language and the context of where these words are being used. All right, that's everything on nuclear reactions. Thanks for being here. Please leave any questions you have in the comment section below the video. Subscribe so you don't miss the next lesson, and I'll see you there. Bye.